Yes. Okay. So once again, welcome to this session. Today I'll brief about whatever was taught during week 7 lectures. I'm sorry if I'm repeating. I just turned on the recording right now. Okay. So before I move into today's problems, do you have any questions? Questions, doubts, feedback, anything? Okay, so if not, we'll just move to the lectures. Okay, thank you. Alright. Okay, so what was discussed this week was the classical linear regression model, also abbreviated as CRLM, the assumptions, and how we can we can fit ordinary least squares if certain assumptions hold, these assumptions if they hold. And we also got to know how should we fit a model when we have two variables, which boils down to a case of a simple linear regression. And also we also got to know what happens. Variables means here I am talking about independent variables. Okay, so if I have a model y equal to alpha plus beta x plus epsilon, then this one is my independent variable or predictor, and this one will be my dependent variable, or also known as, sometimes referred to as, response. Okay, so if there is only one predictor, this will fall in the paradigm of uh, a simple linear regression. Okay, so by two variable I mean both dependent and independent, sorry. And when we have more than one independent variables, then this is typically a case of multiple linear regression, and we got to know how we can get the OLS estimates using some matrix theory, and how to represent the entire regression model using matrix notation. Apart from these, we also saw how we can model different functional forms, how to interpret. So it could be a log-log model or a log-linear model. So if we have something like y equal to x1 to the power alpha, x2 to the power beta, so if we take log y, then it becomes something like this, where the derived equation then becomes linear in terms of the parameters. So another thing that we learned in these lecture sessions were that linearity is always in terms of parameter and not in terms of the variables. Okay, so we learned about different functional forms and how these functional forms, different functional forms could have different interpretation in an econometric setup or context. These we learnt. We also learnt the Gauss-Markov theorem, which stated that if the above assumptions hold, then, so I'll talk about the assumptions briefly. So if some assumptions hold, then the OLS estimates are the blue, that is best linear unbiased estimators. OLS estimators will be blue. Why blue? Because they will be the best with minimum variance among all unbiased estimators. So this was what Gauss-Markov theorem was about. Then we learnt about a few outlier detection methods, like if we have an extreme value in y, then we learned the use of standardized residuals. If we have some influential point or high leverage point, then we learned how to use DF fits. And finally, we learned about some goodness of fit measures like R square, adjusted R square, and Akaiki's information criterion. So with that, we'll move on to the actual problems and their solutions. But before that, I just want to uh, recapitulate what the underlying assumptions were, because this is very important, and in practical scenarios the we should check if these assumptions hold or not. So the first assumption is that the independent variables are non-random. The number of observations in the sample is greater than the number of parameters to be estimated. So if we remember a multiple regression model, then we would have it something like this, plus epsilon. But if you are not aware of this notation, so let's say if I have my y observations on 4 observations, so here n will be 4, and if I have 4 predictors, then p's, or let's say 3 predictors, then also this is not going to, I mean, or to be very now if we want to fit a model like y equals to alpha plus beta 1 x1 plus beta 2 x2 plus beta 3 x3, then we have 4 parameters in the model. So here p will be 4, and we need at least 5 n's to get the estimates of these 4 unknown parameters. So the first thing is that the total number of observations n should be greater than the number of parameters to be estimated. The second thing is that the x values, they are non-random, they don't follow any distribution, and the values are fixed. A linear model is always linear in parameters. So if we have something like y equal to alpha plus beta x plus beta x square plus beta 3x cube, this will work. This is also a linear model because these unknown parameters do not have any power associated with them. But suppose if we have something like y equal to e to the power alpha plus beta x plus beta 1 square y, then this is a non-linear model because this is not linear in parameter, this is not linear in beta 1. Okay, is the difference clear? Okay, so moving on, then the other assumption was that the regressor variable values are independent of the error term, that is each covariance of xi and the errors are the covariance between the predictor and the errors is 0, and also expectation of epsilon I for any x is 0, and for all values of x or for any x, variance of epsilon should be sigma square, and there should not be any serial correlation between the error terms. So covariance between any 2 error terms should also be 0. Now these two are serious assumptions, and when these assumptions are violated, then the OLS estimates do not work properly, in the sense that they are not the best ones to use. So then we have to use some modifications, so we have to make some modifications and do those calculations. So this one will be covered in week 8 and 9 lectures. So just keep this in mind that we should be careful about these assumptions. Okay, so with that I will move on to the questions. So first I will just provide the solutions of week 7, and then we will discuss some other questions. Okay, so this is the first one. We have 4 questions in the OLS context, and we have to choose which are the correct ones. So what do you think the correct ones are and why? Okay, so if you remember here, let us consider that initial thing from where we started, yi equals to beta naught plus beta 1 xi plus ui. This was my model from where we started. So the logic was to minimize the error sum of squares. So what we did, we took this one yi minus beta naught plus beta 1 xi, then we did a square, then we took summation over all values of I. This was my s, and we had to minimize. Now what was the minimization? How did we do this minimization? We took partial derivatives with respect to the unknown quantities, and then we equated them to 0, and then by solving these two equations we got beta naught hat and beta 1 hat. So if we put the values of these things with beta naught hat and beta 1 hat, then this quantity should be equal to 0. Just back tracing. Am I making sense? Is it clear? Because we had obtained these estimates by equating the partial derivatives to 0 and solving for them. If we have the partial derivatives and just instead of these unknown values, if we plug in whatever we had gotten, we would ultimately land up at 0. So these are essentially nothing but the normal equations. So once again we will do del s del beta naught, del s del beta naught would be differentiating with respect to beta naught. So we will have summation 1 I equal to 1 to n 2 of yi minus beta naught minus beta 1 xi into coefficient of beta naught, that is minus 1. So which is essentially the same as I equal to 1 to n 2 yi minus beta naught minus beta 1 xi minus 2 into. So now if we put beta naught hat and beta 1 hat in this equation, we would again get 0, because that is how we derived it in the first place, right? So then if we let us put in at beta naught hat and beta 1 hat, then what will we get? Summation I equal to 1 to n equal to 0. This entire thing will be equal to 0. So now if the entire thing is equal to 0, then summation I equal to 1 to n yi minus beta naught hat minus beta 1 hat xi, this would also be 0, and this is nothing but my ui hat. Ui hat is yi minus beta naught hat minus beta 1 hat xi. So that is why this one is true from the first equation. So similarly, from the second equation we would have So similarly here if we do del S del beta 1, then that at beta naught hat and beta 1 hat, that will also be 0. So then that would be 2, because our model is this beta naught plus beta 1 xi plus ui. S is summation I equal to 1 to n yi minus beta naught minus beta 1 xi square. So 2 will come again here, yi minus beta naught minus beta 1 xi into coefficient of beta 1, that is minus xi. So if we put this thing yi minus beta naught hat minus beta 1 hat xi into minus xi, then we would get this to be 0. So if we put minus 2, if we divide everything by minus 2, then we would have summation xi yi minus beta naught hat minus beta 1 hat xi will give 0, and which is the same as summation xi ui hat equals to 0. So this is also correct. Is it clear? Any questions? Okay, so just remember, when you have two variables, these summation ui hat equal to 0 and summation xi ui hat equal to 0, these will hold. When beta naught and beta 1 are the OLS parameters. Okay, so we will then move on to the next part. Okay, so which of these do you think is correct? So if we just check the first one, then yi equals to beta naught plus beta 1 xi plus ui. This is correct. Why? Because this is the population regression line, where this part is the systematic part or expectation of y given x, and this is the random or error part. Okay. Why this is not correct? Because this is yi hat, yi predicted. Yi predicted will always be beta naught, because this is predictions, nothing should remain unknown. Just plugging in xi should give me yi hat, but here beta naught and beta 1 are unknown. Whenever we have hat above them, then those values are known, those are the estimates. So this is wrong, this is right. Again this one, why is this correct? So this one is correct because yi equal to yi predicted plus ui predicted, because ui predicted is nothing but yi minus yi predicted. This one holds. Okay. Observed yi is whatever I am able to predict, and whatever I am not able to predict, I am putting it as residuals. So both of these will add up to yi. So if we expand on this, then yi equal to beta naught hat plus beta 1 hat xi plus ui hat. So this is correct. And why this is not correct? Because yi hat is the prediction. So here we will, this is the predicted y. We don't want, if we put this one and this one, then this is actually yi and not yi hat. Yi hat will always be beta naught hat plus beta 1 hat into xi. Okay, is it clear? Shall I move on to the next one? Okay, okay. Fine, then moving on. Can we apply OLS to the following model? So here we see that the variables, this is a nonlinear variable. This is also a nonlinear variable. But what about parameters? Are they linear or non-linear? Parameters mean, yes, the beta naught, beta 1, beta 2, beta 3 and beta 4. All of them have power 1. So they are all linear. We have no problem in fitting OLS. Now we have to check, this is with the implicit assumption. This just keep in mind that those assumptions that we mentioned, they hold. I mean, we can anyway apply OLS, but it will not be a what do I say, the correct thing to do. We can do it because these are linear in parameter, but we could do something else which would give us better results also. So this is just a caveat that you should keep in your mind. Okay, this is beyond like exams. Okay. So here we have data on x and y. We have been asked to fit the regression of expenditure on a family income, and there are no other variables involved. We are just going to use a simple linear regression model, and we have to find out the estimates of beta naught, beta 1 and r square. So if we remember the formula, then beta 1 hat is nothing but summation xi minus x bar whole square, sorry, xi minus x bar into yi minus y bar divided by summation xi minus x bar whole square. We can write this as sxy by sxx. Okay, and beta naught hat was y bar minus beta 1 hat x bar. So now we have to find out these quantities and the sum quantities. Now in order to do this, we can apply some shortcut methods so that the derived variable would have x bar and y bar as 0. So if we want to do this, I will just write it here. Okay, so the first task is to find out x bar and y bar. So y bar will be how much and x bar will be how much? Can you please calculate? How many observations do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 total observations. So n will be 9. Okay. So what is x bar and what is y bar? What did you get?
is 177.77.
Okay, 177.77. Okay, I got something different. And y bar, how much did you get? Okay,
Yeah,
so
ma'am. X
this is
bar is
10.
170. Acha, number of observation is 10.
Number of observation is 10. That is what I'm saying.
170.
Yeah,
X
sorry.
bar.
So this is uh, x bar is 170. This is 10. Here we have 170. What is y bar? It come to something around 111. It should come 111. Did you get it? Yeah. This is 111.
Yeah,
Are you
111.
getting it? Okay.
Yeah, yeah.
So once we have y bar and x bar, when we are calculating this thing, xi minus x bar, yi minus y bar, this is the same thing as calculating if we have a variable like this. If we do yi minus y bar here, let us name it as y prime, and xi minus x bar here, let us name it as x prime. So then this will be 70 minus 111, that is minus 41. 65 minus 111, that is minus 46. 90 minus 111, that is minus 21. 95 minus 111, that is minus 16. 110 minus 111, that is minus 1. Then we have 4, 9, 29, 44 and 39. Okay, and then we have this one as 80 minus 170, that is minus 90, minus 70, minus 50, minus 30, minus 10, 10, 30, 50, 70, 90. So then y minus y bar into x minus x bar would be 3690, 3220. We'll just multiply these two columns. 1050, 480, 10, 40, 270, 1450, 3080 and 3510. Okay, so we have this one. What else do we need? We need x minus x bar square. So this will be 8100, 4900, 2500, 900, 100, 100, 900, 2500, 4900 and again 8100. So then beta 1 hat would be, we'll add this up divided by this one. How much is this coming if we add up? So this will come up to 16800, and this will add up to 33000. So then beta 1 hat is 16800 by 33000. This will be 0.509. Are you getting this? Okay. I hope all of you got this. Then what will be beta naught hat? Formula is y bar minus beta 1 hat x bar. So we'll just plug in x bar, y bar values over here, and we'll get it like 111 minus 0.509 into 170. So how much is this coming? $24.45. Okay. It's actually 47 if we use these values. Okay. $24.47. So this is the answer to part B. Now they've asked this thing. What is the value of r square? So to calculate r square, r square is what? It is the explained sum of squares divided by total sum of squares. Now this one is beta 1 hat square into sxx by syy, or in other words, beta 1 hat square summation xi minus x bar whole square divided by summation yi minus y bar whole square. So this is the formula for r square. So now if we go here, here, we also have to calculate y minus y bar whole square. So let's do it. Then this will be 41 square, that is 1681. Then we have 46 square, 2116. Similarly 441, then 116 square, 256, then 1, 4 square 16, 9 square 81, 29 square is 841, then we have 44 square 1936, then we have 39 square 1521. So now if we add everything up, how much are you getting? Should be something around 8890. Are you getting this? Yes, 8890. Alright, then we'll just plug in the values over here. So here what we have, 0.509 whole square into summation xi minus x bar square was 33000. So this is 33000 divided by yi minus y bar whole square, that is 8890. So this would come around to 0.961. Are you getting this? Okay. Alright, then I'll move on to the next question. I hope everybody got this. Okay. Fine. So then we'll have this one. So do you remember how we can calculate standardized residuals? What was the formula? So if I denote this by di, then it is actually the observed value of the response minus the predicted value of the response divided by root mean of sum of squares. Okay, so this is the formula for calculating standardized residuals. Now we have been given a model where they have done the job for us. They have already calculated using these variables. So fitting y, regressing y on x1 and x2, the fitted model comes out to be this, and the sum of squares of residuals also they have calculated is this thing. So then we have to find out what is the third standardized residual, D3, which means if I have 1, 2, 3, 4, D3 corresponds to, this is just notation, corresponds to what will be the standardized residual for the third observation. So we will focus on this third row. Is it okay? Okay. So one request I have, can you please, since there are not a lot of people, can you please unmute and say that if it is okay or not, so I don't have to go back and forth then every time. Alright. So we'll just start with it. So y, so when we are asked D3, we would need y3 minus y3 predicted by root over ms residuals. Now we have this model. Okay, so ms residuals will be SS sum of squares due to residuals divided by n minus p or k, where k is the number of parameters estimated. So here what is the value of k? Anyone? k is the number of parameters estimated. So k is essentially this equation. Note that this is yi hat. So y would have been some alpha plus beta 1 hat x1 plus beta 2 hat x2 plus epsilon. Here we have alpha hat as 255.21, beta 1 hat as 2.47 and beta 2 hat as 0.9. So 3 parameters they have estimated. So here k is 3. And how many observations? So can we fit a linear model? Yes. Why? Because 3 is less than or n is greater than 3. We have n equal to 4 observations. So then if n equal to 4 and k equal to 3, my ms residuals will be ss residuals divided by 4 minus 3, which is essentially the ss residual itself. Okay. So then we would have this as y3 is 327 minus predicted value of y3. So that will be, how will we get this predicted value? Using this regression equation. So then what we would write, this would be 255.21 plus 2.47 into x1 was 15 plus 0.9 into x2 is 32. So this entire thing divided by square root of ms residual is the same as ss residual, ss residuals. So and that will be we will just plug in the value 52.43. So how much is this coming? So this is coming as 5.94 divided by square root of 52.43 is that is 7.2408. So if we just divide 5.94 divided by 7.2408, this is close to 0.8. Is it okay? So now if someone asks, is it an outlier? Then what will be your answer? So the answer is it is not likely to be an outlier because the standardized residual is close to 0, and if it goes beyond 3, because we believe that the error or the residual thing much later, for this fitting we don't need any distributional assumption, but for carrying out testing we do this assumption that the error or residuals are normally distributed. So if we have this value beyond -3 or +3, then we can say that this can possibly be an outlier, even though there are other techniques to confirm, and if we use like 2-3 techniques and all give me the same answer, then I will be more sure that whether this is an outlier or not. Okay, but since this value is very close to 0 and is within plus minus 3, this is not likely to be an outlier. Is it okay? Okay. So, okay, moving on. So, suppose we have this model which we want to fit using 20 observations. So, n equal to 20, we have 20 y x1 x2, 20 such tuples, I will say. Okay, this information for 20 individuals. So, in order to identify possible influential observation is that which is of, let's say if we have a scatter plot, if we have an x value which is very extreme, such that the usual range is, let's say, between 1 to 3, but this x that I have is here, okay, very extreme. Let's say this is something around 10, but it is not likely to affect my regression line because it falls like close to the regression line. It is not changing the pattern. So, those points are just leverage points. But if I have something like this, let's say something very odd in x or very odd in y, such that the if this is the true regression line, the pattern altogether is observed. Like if we have something like this, then this line in the presence of this one will become deflated. They will change the regression line. So, such observations are usually known as influential observations. Now, how are these influential observations, like high leverage outliers or outliers in x or y which change? So, the actual definition is outlier in x or y which change the regression equation drastically. Okay. So, the formula to calculate df fit is yi hat minus y of minus I hat divided by standard error of yi hat. Okay, where yi hat is that we will fit another regression excluding the line I. So, what I mean to say is that, let's say I have this scenario where this is my regression line with all points. This is the true one, but in the presence of this point I have this line a little deflated, or let's say this one. Okay, and if I remove this one, so whatever this line, from this line whatever I am getting is my yi hat. Okay, if we from the green one whatever we are getting, this is yi hat. Okay, now if we just leave the ith let's say this is the ith observation. Okay, so if we leave this out, then we will have just this line. So, whatever is this predicted line, this is y minus I hat. So, df fits is calculated as yi hat minus y minus I hat by standard error of yi hat. So this will be calculated, since this is a leave one out thing. For all the observations, this has DF fits have to be calculated. So how many observations do we have here? We have 20 observations. So total number of DF fits that can be computed is 20. DF fit 1 will be all y hat minus y hat except observation 1 divided by standard error. Similarly, DF fit 2 will be all keeping everything y hat minus y hat that is estimated, removing observation 2. The logic is, if this one and this one is actually, if this is not an influential observation, then it will follow somewhere close to this line. So the difference between this line, this point and this point in the y axis will not be much. See, this will be small. But if this is changing the trajectory, if it is changing the regression line, then this y hat at, so what I am trying to say is that I think I put an arrow in a wrong direction. This arrow yi hat is here, okay. This is yi hat with respect to this green line. This is yi hat. But leaving this one, then it is somewhere here. So if the differences are more, then the diff fix values will increase. So this is the concept or the logic. The question says how many should be computed. How many number of observations are there, those many number of DF fits need to be calculated. So the answer is 20. Is it clear? Any confusion, any doubt? Please ask me. Anything? Okay, then I will proceed. So the main thing is the number of observations that we have, so many number of DF fits you can calculate and see if each of the observation can be an influential point or not. Okay, moving on. So here they are saying that the price of a house could depend on age of the house, distance from floor, the floor area, the locality, distance from nearest hospital. So these are 4 parameters on which a price of a house could depend on. So the first thing is that how many regression models can we have if it is given that a beta naught term is included in all the models. There is a table which will come soon. The residual sum of squares for all possible regressions is given below based on 13 houses. So the first question that I want to know is how many regression models can we have. So y equal to beta naught is always present. So it could be y equal to b, if we include just one, it could be x1, it could be y equal to beta naught plus x2, it could be y equal to beta naught plus x3, it could be y equal to beta naught plus x4. So if we take 2 combinations, then it could be beta naught plus x1 plus x2, it could be beta naught plus x1 plus x3, beta naught plus x1 plus x4, beta naught plus x2 plus x3, beta naught plus x3 plus x4, and so on. We can take combinations and see. So, but since the numbers are small, it's not an issue calculating so many regression models or finding out how many regression models can we have. But if it is a large number, then it would have been a problem. So, how will we get this? So, here what are we doing? Here we are not selecting any of the 4 covariates. So, how many ways we can do that? Not selecting anything from 4, we can do it in 4C0 ways. Then we are selecting one variable out of the 4 choices. So, then that is 4C1, we can do it in 4C1 ways. Choosing 2 variables out of 4 variables can be done in 4C2 ways. Similarly, choosing 3 variables from a list of 4 variables can be done in 4C3 ways. And finally, if we choose all 4, then we will have 4C4, that can be done only in 4C4, that is one way. So, this is 1 plus 4 plus 4 into 3 in. So, how is this calculated, this combination thing? NCR is nothing but n factorial by r factorial n minus r factorial. So, here we will have 4 factorial by 0 factorial into 4 minus 0 factorial, okay, and 0 factorial is always 1, keep this in mind. So, here what we have, these 4 factorial will cancel and we have 1. So, here we have 1 plus similarly 4 factorial by 1 factorial into 3 factorial. We can write this as 4 into 3 factorial divided by 1 factorial into 3 factorial. 3 factorial cancels, 1 factorial is also 1, and similarly 4 factorial by 2 factorial into 4 minus 2 factorial plus 4C3 is also 4 factorial by 3 factorial into 1 factorial, and again 4 factorial by 4 factorial into 0 factorial. So, what we are getting is actually this. This is 1 plus 4 plus 4 factorial 4 into 3 by 2 plus 4 plus 1. So, this is nothing but 6, 6 plus 4, 10, 11, 12, 13, 14, 15, 16. So, altogether we will have 16 models. Also, if we have something like this, like NC0 plus NC1 plus dot 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 plus NCN, that is essentially 2 to the power n. Okay, this is also one shortcut formula. So, here we had n as 4, 4C0, 4C1, 4C2, 4C3, 4C4. So, it will be 2 to the power 4, that is 16 total models. I hope this is clear. Previously someone had some problem regarding this factorial calculation. So, please remember, I am using this shortcut 4 into 3 by 2 because it is only, the difference is only 2. This is not always applicable. The correct formula is n factorial by r factorial by n minus r factorial, and n factorial will be n into n minus 1 into n minus 2 into dot 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 2 into 1. Okay. Is this clear?
Clear, ma'am.
Okay. So, now that we know that we can have 16 regression models, they have calculated and given us residual sum of squares for all possible regressions based on 13 houses, that I am going to show in the next slide. So, this is the meaning. Okay. None means they have only fit y equals to beta naught or something. So, it does not make sense y equal to beta naught. This is actually the sum of squares of residuals is, we are not including any of the covariates as something. So, this sum of squares residuals where none of the variables are fit, this is essentially y bar minus this thing, summation yi minus y bar whole square, or SS total. If you remember this identity, SS total equal to SS due to regression plus SS due to residuals. Now, regression term, this will only arise when we have some regressors in the model. When we have none regressors, that means this part will be 0. So, SS regression is actually SST. Is it clear? Okay. So, if we take any random model, let us say we will take this one, this means that we have fitted y equals to alpha plus beta 4 x4 plus epsilon, and then we got some y hat equals to alpha hat plus beta 4 hat x4. We calculated y minus y hat, summed it up, and we got some SS, we got this SS residuals as this value 650.76. This is the meaning of row 5. Okay. Is this part clear? Then we will move on to the question. Okay, I think this is clear. So, then the question is, the value of coefficient of multiple determination r square for this model is approximately equal to how much? So, we know r square is sum of squares due to regression by total sum of squares. This we can write as 1 minus SS residuals by SS total. So, then when we have x2 and x3 in the model, then we will be focusing on which column? We will be focusing on, which row? We will be focusing on this row, because this model is fitted with x2 and x3. These are the regressors, and from that model we are getting this SS residual. So, then we will just plug in values. This will be 1 minus 374.34 divided by sum of squares total is what? When we did not fit any of the regressors. So, then that is 2514.87. So, then what is this value coming out to be? So, this is something 0.85. Okay, that is approximately equal to 0.85, which is the coefficient of determination for this model. Is it clear? Okay, fine. So, moving on. Okay. So, okay. So, the value of Rp square for this model beta 2, x2 and x3. So, the focus remains the same, x2 and x3. We have to find out this one. This is nothing but adjusted r square. Okay. Just ignore this notation. This means adjusted r square. Now how will we calculate adjusted R square? What was the formula? Adjusted R square is nothing but one minus SS residuals divided by degrees of freedom by SS total by degrees of freedom. Okay, this is one formula. The other one is adjusted R square. These are all interchangeable. 1 minus R square n minus 1 by n minus k minus 1. Okay, where this k is the number of predictors, or rather number of regressors. Okay, so we can use any of the two formulas. First, let us use the second one. So R square value we got something around 0.85, n is 13 they have said. K is how many regressors are we using? 2. So how much, using this second formula, how much is the adjusted R square? Can you calculate? If we use this, 1 minus R square was 0.85. So this will be 0.15 into 12 divided by 13 minus 3. 1 minus 0.15 into 1.2. How much is it coming out? It is coming something 0.82. Okay. The alternative way, if we want to calculate, then actually this reduces to this formula finally. But anyway, we will also calculate from this table. So total sum of squares will always have df n minus 1. Total sum of squares is this thing 2 5. I'll just copy 1 second so that it's easier. Okay, so using the second formula we have calculated, it is coming out to be 0.12. So if we use the first formula directly from this table, then how can we get it? Okay, so see, sum of squares residuals with x2 x3 was this value 374.34. Okay, so we would have this as 374.34. By degrees of freedom, I am coming to it. Now SST will also always have degrees of freedom n minus 1. So n minus 1 will be 12. Okay, and sum of squares total was this one, where none of the variables are fitted. So this is 2514.87, and degrees of freedom of error or residuals is always n minus number of parameters estimated. So here we had 1, 2, 3, beta naught, beta 2, beta 3, 3 parameters. So this is 13 minus 3, that is 10. So if we compute this, if we check with this one, it's almost similar. 0.015 is that value, r square value, which is this one, and this will become 12 by 10 into r square, because this one was the r square value. Okay. So these two are equivalent formulas. You can use either one of them. Just we have to ensure when I am writing this formula, k is significant of the number of regressors, and since when I am writing this one, the degrees of freedom is the total n minus total number of parameters estimated. So here we had 2 regressors and one intercept term, that was accounted for by this one. Okay. Is it clear where the distinction is, where we have to be careful? If we are using this formula, we have to make sure that we are counting k as the number of regressors. Is it okay? Shall I move on to the next one? Okay. Here we have another question. So we have x and y. We've been asked to get the r square and adjusted r square manually. So same thing, let's say this is my model. From here I am going to get beta 1 hat as summation xi minus x bar yi minus y bar by summation xi minus x bar whole square. Alpha hat I am going to get as y bar minus beta 1 hat x bar. From these two I will get the SST summation yi minus y bar whole square. We will get the SS residuals, that is, or rather we will get SS due to regression as beta 1 square summation xi minus x bar whole square, and then we will get r square as SS regression by SS total, and we would get adjusted r square by 1 minus, what was the formula, 1 minus r square by n minus 1 divided by n minus k minus 1. Here k would be 2, sorry, k would be 1, because k corresponds to regressors and here we have only 1. So if we just use this table, formulate, and then we will get everything as 1. And one more thing, here n is 1, 2, 3, 4, 5, 6, 7, 8, 9. Is it okay? It's the same sort of calculations. I am going to, so finally we should get r square and adjusted r square as given in like the answers should be whatever is mentioned over here. Okay, that's the answer that you should get. Alright, moving on. So we have fitted this model. We want to know if the model will be improved if we add x4. So there are two ways to go about this. We can do a formal testing whether my model is improved, or like here they are saying if the model is improved. So we have to diagnose and find out if the model parameters, which will give us some goodness of fit measure, that is going to improve the model or not. So what we will do, we had, so from the previous one, R adjusted R square came out to be something around, what did we get? What was the value of adjusted R square? What did we get it here? 0.82 with x2 and x3. If I am not wrong, with x2 and x3 we got, yes, 0.82. Okay. Now we want to know if the model is improved if we add x4 to this model. So now currently we are going to add x4 to the model. So we will be focusing on x2, x3 and x4, that is this number. Okay. So now we will have y equal to beta naught plus beta 2 x2 plus beta 3 x3 plus beta 4 x4 plus epsilon. So then here k becomes 1, 2, 3. Okay. R square will remain the same. What do you think? Will the R square remain the same as it was last time? What do you think? Okay, no response. So the previous R square was based on that model y equal to x2 plus x3. That R square had some, like, R square is what? Explained variance, sum of squares due to regression by sum of squares total. Now when I am adding more variables, this R square value is going to increase, right, because more of the total variation is being explained by addition of a new variable. So that R square and this R square is not comparable. Okay. So for each model, when we add another covariate or another predictor in the model, the R square values will also keep changing. So then here R square will be 1 minus sum of squares due to residuals from the current model by sum of squares total. So then this is total, this is correct model. So R square will be 1 minus 77.25 by 2514.87. Okay. So how much is this coming to? This is 0.97 approximately. Okay. Previously it was 0.85. This is 0.97. Now we have to find out what is the adjusted R square for this model. This was for the previous one. Now this one is 1 minus R square into n minus by n minus 1. Oh sorry, into n minus 1 by n minus k minus 1. sorry, this is divided by. Okay. So then how much is this coming out as? 1 minus 0.03 divided by n is how many? 13, that is 12 by, sorry, this is not divided by, this is into. I'm really sorry. Divided by 13 minus k is how many? 3 minus 1. So 1 minus 0.03 into 12 by 9. So how much is it coming to? So this is also coming to 0.96. So previously it was adjusted R square was 0.82. Now the adjusted R square is increasing. Thus the answer is yes, the model will be improved if we add x4 to this model. R square will always increase. If we include 5, 6, 7, 8, R square will keep on increasing. But adjusted R square will not increase beyond a certain point. Okay. So when we have to figure out which we should use, which metric we should use, we should be judicious and we should choose or prefer adjusted R square over R square, because adjusted R square associates a penalty with the increasing number of regressors, and then even if with that penalty it is giving me improved results, I am going to add extra covariates to the model.
Ma'am, in this question,
Yes.
why we are not using the divide sign? 1 minus I square upon n minus 1. In the previous
We use divide square. What are we getting? So see, n minus 1 is this, actually this df. If I come from this one, adjusted R square is 1 minus SS residuals by df residuals by SS total by df total, which is always n minus 1. So we can write it that SS residual into n minus 1 by SS total into df residuals. So this is 1 minus this thing is R square into n minus 1 by df residual is actually n minus k minus 1, the same thing. Sorry, this is 1 minus R square. R square is SS regression by SS total, or 1 minus SS residuals by SS total. Are you getting this? Is it understandable?
yes, ma'am.
So in the previous one, if I have written divided by, then I have,
Example number 8.
in example 8 I have written that. Okay, so that was
1
wrong.
minus R square upon n minus 1.
Okay. So here I wrote, oh okay, this is wrong. Here also I've written correctly. This is the equivalence thing. It's clear? No. Okay. I'm sorry, that was a mistake on my part. Alright, so then I'll move on to the next one. So similar sort of question, what is the coefficient of multiple determination for this model x1, x2 and x4? Similarly, R square will be 1 minus SS residuals divided by SS total. SS residual 124 is this one, 43.24, divided by total, that is 2514.87. How much will this come to? This will be 0.98 approximated to 2 decimal places. Okay, I'll just move on to the next one. Before that, my laptop is running out of charge. I'll just plug it in. Okay. Alright. So, let's see question number 12. We have a set of variables we have three regressors, one, two, three, four parameters, and this data matrix. So, can we fit OLS? Should we fit OLS? The answer is no, because the assumption is n greater than p. That will give us a unique fit to the model. But apart from this is one criteria. The second criteria is for not getting a unique fit to the model. So, if we have n greater than p, if we get rid of one of the variables, okay, so then we can fit a model to this one. If we can get rid of one of the parameters, then we can fit a model. Now, there was something sir talked about, a concept of multicollinearity. So, from these three columns, the x columns, okay, will it be possible to see if these are linearly dependent or not? So, if we look carefully, then if we do half x1 plus 3 by 2 x2, then we are getting x3. We put 5 here, half into 5 plus 3 by 2 into 5, that is 2 into 5, 10. 2.5. So, here again if we go to the second one, 5 by 2 plus 9 into 3 by 2 is how much? 27 plus 5, 32 by 2. This is also coming to as 16. So, these three columns are perfectly linearly related with these formula. So even if we would have had, let's say, something else, if n would have been greater than 4 and this equation holds, there is perfect multicollinearity, then also we would not have been able to to get a unique fit to the model. Why? Because if we go in a multiple linear regression concept in that framework, so if we write it in a matrix format, let's say n cross p beta p cross 1 plus epsilon n cross 1, then beta hat is x prime x inverse x prime y. This inverse calculation this requires n to be greater than p and rank of x to be exactly equal to p. Okay, so what essentially happens, if I have dependencies like these, then in the presence of dependencies between the p columns of X matrix, what happens is that rank of X becomes less than p, and this inverse is then is not unique. Okay, so for the inverse to be unique, the rank of X should be equal to p. So anyway, here even if we would have had more data points, if this relationship is satisfied, we would not get unique fit to the model. Now the question is what to do. So what we will do, if these three are perfectly correlated, we can drop one of these variables. So let's say we drop x3, because x3 essentially contains the same information as x1 and x2. So then we would have p equal to 4, n equal to 4, and then we could have fitted a OLS model. Now another question is, how would we know? Because here by looking at it, and because I know, it is readily noticeable to me. But if it is not, then what will I do? So let's say if we have beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x4 plus epsilon, let this be the model. This is y1, y2, 1 1, 2 1, 4 1, e1. Beta naught plus beta 1 x 1 2 plus beta 2 x 2 2 plus beta 4 x 4 2 plus epsilon 2. So let's say we have n such individuals, so we will have n such equations, x2n plus beta 4 x 4n plus epsilon n. This thing we will just write in a matrix format. Yn equal to 1 1 1 1 1, all columns will be 1. This will be x11, x21, x41, x12, x22, x42, and so on, x1n, x2n, x4n into beta naught, beta 1, beta 2, beta 4 plus epsilon 1, epsilon 2, epsilon n. This is the same as y n cross 1 equal to x beta, where this is n cross p, p cross 1. Here p, let's say, is 4. number of parameters to be estimated, plus epsilon n cross 1. So if I have a equation or a table like this, I am going to get the model matrix like this. So here if we go here, we have some values, right, of x1, x2, x3, y. So let's say we have dropped x3 because that way it is not possible. So what we will do, the model matrix will be 1 1 1 1, then we will have x11, x12, x1n, and let's say this is x11, x12, x1n, some values. Okay, so we will just put x21, x22, x2n, and then we will check if there are some dependencies between these two or not. Okay, one of the things near perfect, we can check the paired correlation between each of these two variables. That is one way to check. If it is very high, greater than 0.9, then maybe we should drop one of the variables. Okay, or we could do, like if you remember while doing determinant calculation, what we did, we took some linear combinations and then we would try to make as many zeros as possible and then get a short reduced form and then get that determinant. So the main thing is why this inverse should exist, a unique inverse, because x inverse is what? It is adjunct of x by determinant of x. If this quantity should be non-zero, and that is only happen when the rank of this X matrix equal to the total number of unknown parameters. Okay, so we have to see that using any linear combination, plus minus multiplication into scalar, if one of the columns get totally 0, that means perfect multicollinearity, then we have to drop it. Like we said, here we have the exact linear relationship. Even if we don't have a linear relationship, we could check pairwise. So between if let's say x1, x3, x3, x4, something is like that, we could check pairwise correlations between these, and then we could have taken a decision. So these are like all diagnostics or exploratory analysis that we should do, so that there is very little or no multicollinearity in the sample, because if it is there, then it no longer the OLS estimates do not remain minimum variance. That is one criteria. Why is it important? Because we want our estimate to not vary too much. We want precise estimate. For that precision, the variance of that estimator should be low, and that is not ensured when we have problems like multicollinearity in our models. Okay. All right. So then I am going to move to the next question. So the effect of temperature of the deodorizing process on the color was determined. We have to find a 95% confidence interval for expected response at x equal to 0. So I'll try to derive the mathematics, but I don't think such extensive mathematics will be needed for you. The final form you should be able to remember. So if we have a model like this, beta 1x plus epsilon, expected value is beta naught plus beta 1x, because you remember expectation we assume to be 0 in one of the assumptions. This one, expectation of x will be 0. So now when we have expectation of y given x equal to x naught, here x naught is 0, okay. This is x naught. Then it becomes beta naught plus beta 1 x naught. We are substituting this x value with x naught because x is given. Now we have to find out a confidence interval for this quantity, okay. So now if I suggest my estimator, which will be unbiased, it has been seen, is beta naught hat plus beta 1 hat x naught. This is my estimator. So expectation of this thing equals to beta naught plus beta 1 x1, which is expectation of y given x equal to x naught, okay. And then variance of this thing would come out to be sigma square 1 by n plus x naught minus x bar whole square by sxx. So this might be a little difficult to understand at first. I'll just give you the final formula so that it is easier, okay. uh, so whenever we are asked for confidence interval for expected response at x equal to x naught, 95% CI, this is usually beta naught hat plus beta 1 hat x naught plus minus t n minus 2 root over ms residuals 1 by n plus x naught minus x bar whole square by sxx. So this is the formula, okay. So now x naught is given as x equal to 0, so we are going to plug in 0 over here. So then we would have beta naught hat plus t n minus 2 alpha by 2, because both sides we have to take. Here alpha is 0.05 into root over ms residual by 1 by n plus x bar square by sxx. What is sxx? It is summation xi minus x bar whole square, and ms residual is what? Summation yi minus yi hat whole square divided by n minus 2, that is the degrees of freedom, because we are fitting so two unknown parameters, okay. So from here we have to calculate, like I said, beta naught hat is y bar minus beta 1 hat x bar. Beta 1 hat is summation yi minus y bar xi minus x bar by summation xi minus x bar whole square. Once we get beta naught hat, we'll plug this value here, we'll get beta naught hat, and then we need t n minus 2. So from the t table we'll take n minus 2. How many are here? 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15. So t n is 15, so we'll take it from 13, 0.025. so we are going to take that. If this is a t distribution, we are going to take these positions such that the area below here is 0.025 and the area above here is 0.025. If this is let's say some point q, this will be minus q because t is symmetric about 0. So this one we have to find out from the t table, and x bar we can find out from this here, okay, and ms residual once we get beta naught and beta 1 hat, yi hat will be beta naught hat plus beta 1 hat xi. We will calculate. Ms residuals will be summation yi minus yi hat whole square divided by n minus 2, and just we'll sxx will be summation xi minus x bar whole square. We'll plug all these volume here and we'll get a 95% confidence interval with this formula. When we have just one regressors. Is it okay? Alright, then I'll move on to the last question for today. So this will be like not something where we have to solve, but if we are displayed some results, how are we going to infer from that? If so, each of the software that we are going to use outputs a lot of summary stats with all these values. So what to do and how to infer things from those outputs, that we'll see from here. Okay, so this problem is actually modeling demand of butter, and it's assuming that the demand for butter or the purchases that can be made depends on its own price, then the price of margin in the real income of the people, or yes, and the costs incurred in advertising for both butter and margarine. So this is some hypothesized model that has been given to us. Now from the initial results, it is believed that butter and margarine advertising do not change demand, and income elasticity of butter is 1. Since this is a log-log model, left hand side also is log, right hand side also is log, then income elasticity of butter is actually beta 3. So this is my H naught. H naught is butter and margarine advertising do not change demand. So then if this is not changing demand, then the H naught value is actually beta 4 equal to 0, beta 5 equal to 0, and beta 3 is 1. This is my H naught with 3 restrictions. So if we have to test this thing, this model is my unrestricted model. under H naught, whatever we have, that is known as the restricted model. So then the model becomes ln of butter purchase equals to alpha plus beta 1 ln of price of butter plus beta 2 price of ln of beta 2 of price of margin in plus ln of real income plus beta 4 and beta 5 is 0, so u. Now if you look carefully, this is one observed thing, no constant involved. This is also an observed thing, no unknown thing involved. So what we can do is we can rewrite and devise a new dependent variable, that is ln of butter purchase minus ln of income. This one we can model as alpha plus beta 1 ln of price of butter plus beta 2 ln price of margin in plus u. So this is my restricted model. Now to test for H naught, we need residual sum of squares from unrestricted model minus residual sum of squares from the restricted model divided by R, where R is the number of restrictions, divided by residual sum of squares of unrestricted model divided by df of residuals from unrestricted model. Okay, this becomes my F statistic, and the rejection rule is we will reject H naught if and only if F observed is greater than F R df res of unrestricted alpha. So this is the alpha point, upper alpha, so that area above is alpha. So now we have to find out how we can get this. Okay, so see, if this is my full model, then unrestricted residual sum of squares is this one, 0.274, where I am fitting butter purchases on all my, this corresponds to alpha, these are the betas. Okay. Now when I have the restricted model, then from the restricted one, the sum of squares due to residuals is this one, 0.287, and this is 0.274. So then the F observed becomes sum of squares from the sum of squares residuals, sorry, I wrote it this ulta, one second, f stat can never be negative. So this is residual sum of squares from the unrestricted model. No, again I wrote, this is residual sum of squares from the restricted model minus residual sum of squares from unrestricted model by unrestricted model. So here f observed will be sum of squares residuals from the restricted model 0.287, this one, minus sum of squares residuals from full model 0.274 divided by total number of restrictions were 3, beta 3 equal to 0, beta 4 equal to 0, or something I wrote here, beta 4 5 and beta 3 equal to 1, sorry. So it was beta 4 equal to 0, beta 5 equal to 0 and beta 1 equal to 1. So these are the 3 restrictions. So divided by 3 divided by sum of square residual sum of squares from the full model, that is 0.274 divided by the degrees of freedom. So degrees of freedom for this case is 45. So if I look from here, there were n equal to 51. So n minus 1, this is the total degrees of freedom. Residual is n minus how many we are predicting. So 1, 2, 3, 4, 5, 6. N minus 6 we are predicting, that is 45. That is what has been written here. So once we get this, we will have f observed. So how much is f observed coming? That will be same as this thing.
And this table we get from the software.
This one you will get from softwares.
Which software?
This one I don't know, but the exact same information you can get it in R and Minitab, SAS. Yeah, SATA. All these informations, maybe these have been compiled and put together. This I have taken from one textbook, but if you want to code, you will get all of these in R, Python, Stata, Minitab, anything, SAS. All these informations are available. Okay, so if f, so the cutoff is also given f. So f3. So what we have to compare is, we have to compare this with f345 0.05, which is something as 2.81. Now if this value, how much are we getting this? If you can see, how much is the calculated value? This will be something around 0.7. Now since this is, now f observed is less than f critical, so we will not reject, do not reject H naught. And then if we do not reject H naught, what will we conclude? We will conclude that B40, B50, B1 equal to 1, that is the income elasticity is 1 and advertising do not change demand of butter. Is it clear? Any question, any doubt? Okay.
I mean question number 6.
Hmm.
If the number of observation is 21, then in that case, or if the number of observation is here,
Hmm.
20. If it increase or decrease, then what will be?
Same thing, as many number of observations as that many number of DF fix. What we are doing, we are checking each of the observations against what would have happened if we did not have this one. Each of them we have to check, and there is one cutoff. based on that 3 root over k by something, that cutoff is there, no? So in the lectures you'll find that cutoff. So if the DF fit value exceeds that cutoff, then we can say that probably this, let's say DF fit for observation 5 is exceeding that cutoff. So then we can say that fifth observation is probably an influential point which we should not include in our analysis.
Ma'am, in question number 7,
Hmm.
when we draw this table as models,
Hmm. Hmm.
this one,
Hmm.
then SS residual. So
Hmm.
how we calculate this? We have to calculate this for all these variables. We have to calculate separately.
Yes, exactly. For each of the for each of the models, we have to calculate the OLS coefficient separately, get all the equations separately, and do calculate the sum of squares residuals. Because this beta and this beta naught will not be same, no?
Okay.
Hmm.
If this question came in the examination, then
I don't think
we
this
can
will
get
come
it.
in the examination. Even if it comes, it will come in the summarized form, because otherwise it's not possible, no?
It's not possible. Yes.
Uh, just to I mean, give some idea on what we should do if we see something which is not been discussed, in the format of the classroom lectures, just to give an idea. Okay, anything else?
No, ma'am. Thank you.
Okay, thank you so much for joining. And if you have questions, please post in discussion forum. You can also ask me in the next class. Thank you.
Okay. Thank
Bye
you, ma'am.
bye. Good night.